Yes. Okay, so we discussed an FPT, a randomized algorithm for K-path problem. And the question in the audience was a very good one. So this is a randomized algorithm. Is it possible to obtain deterministic algorithm? And the answer is yes. But the answer is it requires some work, and it also requires some deep tools, mathematical tools about universal hash functions. So what is a universal k-universal hash function? Suppose I have a set of a family of functions. So each of the functions, it maps the vertices of the graph into k numbers. And then I say that this function is a k-universal hash function if for every subset of vertices S of size k, there exists at least one function fi from this family, which makes the set S colorful, right? And then the deterministic algorithm will be, we construct a k-perfect hash function, and then for each member of this family, we look for a colorful k-path. We know that, yes, because we know that if we have a k-path, it's a set of size k, vertices in the graph, then because it's a k-perfect hash function, so there should be some function which realize this set, and for this path will be colorful, and then we can apply our algorithm. Yes, so that will be. So what will be the running time of this algorithm, right? So so if we can, if the construction of a k-perfect hash family takes time t, then the remaining part of the algorithm, so it takes 2k n square, and the total running time will be the time we need to construct the family of functions plus the size of the family, because we run this algorithm for every element in the family, and times the dynamic programming. So yes. Definition of the hash function? Yes. So view it this way, right? So what we did for the algorithm, so we just use random coloring of vertices, right? But this time view this function as just coloring of the graph, right? And this is a very huge set of so every function is a coloring. But the magic property of this coloring function is that if you give me any set of size k, I will tell you, okay, there are at least one function such that this function, colors this particular set in all different colors. So it's sorry? Exactly. So far, I'm just saying if it exists, right? Yes. So how to find it? And okay, so this I will just yes. So how to find it and how to estimate the size of this function is a quite non-trivial things, right? So yes, that's there's a paper of Naur, Schulman, Srinivasan from 1995. So this paper give a construction which constructs a k-perfect hash family of size e power k, and in time an exponential e to the k n log n, right? But it's far beyond what I want to discuss here. It's quite non-trivial thing. But you just what I want to communicate that you should know that this randomized algorithm color coding, there are quite non-trivial mathematical tools. You can use them and de-randomize them. You cannot, we don't know if you can de-randomize any randomized algorithm, right? But at least this type of algorithms we can do. Yes. So, and this gives the running time of the algorithm, deterministic algorithm, 5.4 to the k. And then, of course, you can ask the question if you can do something better. And the answer here is yes. But then you have to apply more ideas. Yes, please.
K-perfect. Yeah, what does a k-perfect hash family mean?
What is this k?
Yeah, what's the notion of k-perfect?
K is the number of vertices in the path.
No. So what does a k-perfect hash family mean?
I can construct K. What is a K here?
No, what's the perfect mean? Like, does that mean that there's no collisions or?
Sorry, I just don't understand the third word you're saying. What is, and then what is the third word? What is a K-perfect hash function? Sorry, I still didn't get. What does it mean that it's perfect or?
Yeah. So what does
But this is what that's the question. Sorry, you got me. Should be universal, not perfect. It should be K universal hash function. Yeah, that's. Yes. No. No. Yeah. Yes. Thank you and sorry. That's okay. And another example also of very nice and cute application of randomized methods is the method which is called random separation. Okay, so the example which I will look at is the induced subgraph isomorphism problem. So you know graph isomorphism problem, of course, right? That's one of the most famous problem in graph algorithms, which we still don't know if it's in P or we cannot prove that it's not in P. And so this is a variant of this problem. I have two graphs G and H. And here I have an additional condition that my graph G is of bounded vertex degree. So this bound is delta. And the parameter is K, is the size of the graph H. And then I ask if G contains H, but this time as an induced subgraph. Right? And the parameter here is delta plus V of H. You can ask me immediately why it's delta plus K, or because before we always had to consider parameter K. Why I make life more difficult? Well, I will come to this in a second, because basically, if I want to solve this problem, again, naive algorithm, what will be the naive algorithm? I try, in graph G, I try all possible sets of size K, right? This takes me n to the K, and then I check if two graphs are isomorphic or not. Okay, and to check if two graphs are isomorphic, well, we don't know if it's polynomial, but if you follow the quasi-polynomial algorithm of Babaye, for example, which runs in time n log k, so that should be more than enough to solve the problem in something like n to the power k. Okay, and also another thing is that this induced subgraph isomorphism, it's also a generalization of a clique problem. So if graph H is a clique, then I just asking if my graph G contains a clique of size K. And this problem, well, I do not speak about complexity here, but this K-clique problem, there's a very strong belief that in the community, and there is also the theory which explains why we believe in that the K-clique problem is not fixed parameter tractable. So, and this is actually why the parameter here is not K, but delta plus K. Because the problem will be W1 hard if we just parameterize by K. Okay, so I will give you the algorithm of running time delta power K. And again, it's coming back to the same question when you're asking about heating set. Like 3 heating set is FPT, 4 heating set is FPT, but heating set is not FPT. So this is exactly the same here. If delta is a constant, this is an FPT algorithm. Okay, so the idea is the following. The algorithm is very cute and very simple. Let me just, for simplicity, assume that graph H is connected. It makes my life a little bit easier. What I'm doing, I just color my graph with two colors, red and blue. I color vertices in red with probability 1 minus P. P is just some constant between 0 and 1. And I color blue vertices with probability P. Okay? This is what I'm doing. And then I look at my colorful graph. And then what I do, I delete all red vertices. And I look at every blue component, and I check if this blue component is isomorphic to graph H by using graph isomorphism algorithm. Right? Once again, so the algorithm is very simple. I color my graph in 2 colors. I assign different probabilities to different colors. And then I just remove one color, and I claim that at least one of the components in my graph should be isomorphic to my graph. That's the algorithm, right? The only thing we have to verify, first of all, that the algorithm is correct, and the second, that the running time of the algorithm is FPT. Okay, so my claim is that if G doesn't contain H, then algorithm always says no. And if G contains H, then all the vertices of H are colored blue with probability P to the, okay, sorry. So if G doesn't contain H, right, then whatever we do, whatever coloring we do, we'll not be able to find the graph isomorphic to that. So we always, yes, if we have a no instance, the algorithm also will say no. Okay, suppose that our graph G contains H. Now let's take a look. Let's stare at this H in the graph G, and then what will be the probability that all vertices of graph H will be colored blue? Right? It's graph H. It has k vertices, so it's P to the k. Right? Okay, let's look what is the probability that all neighbors of H are colored red. And now the degree bound comes into game, because how many neighbors of I have a set of k vertices, so how many neighbors are there? Huh? P is, I have 2 probabilities. I color vertices with color blue with probability P. This is probability, and 1 minus P, right? Okay, so I have at most delta times k neighbors. So the probability that all these neighbors are colored red is at least 1 minus P delta power k. Agree? Right? So it means that the success probability means that my graph H is blue, and its all neighbors are red, will be P power k times 1 minus P delta to the k. We are there, right? So for example, if I just take P equal to 1 over delta, then my success probability will be 1 over delta k times 1 minus 1 over delta power delta k. And again, the magic inequality I'm using here, but now I'm using this part of the inequality, right? So I bound this as a success probability as 1 over 4 delta power k. And now you remember, right, what we did for color coding. We have the same type of success probability. So if I run this experiment this number of times, the success probability will be a constant. That's the algorithm. So the algorithm, I run this algorithm 2 to the O of k times, and I repeat the constant. Okay, so this concludes my part of the lectures on basic algorithms. So what I want to say about randomized algorithms. So randomized algorithms, you probably already saw, like mean cut algorithm. They are always extremely cute, and probably that's the cutest algorithms ever, right? Because they're always simple, but it always takes some knowledge and skills to analyze them. That's one thing. So randomized algorithms are simple, but not simple to analyze. And the second thing is also, if you want to de-randomize, sometimes it's also a nice and interesting challenge how to de-randomize your randomized algorithm. But yeah. Okay, so any questions about the basic algorithms? Yes. Yes, and of course, if you want to learn more about parameterized algorithms, try to download this book. You don't have to pay for that. Of course, if you want to buy it. But yeah. No, look, why I don't know, Saket, how much we gain from every copy? I would say 200 rupees, right, from every copy sold. Rupees. Okay, yeah, that's okay. I want to speak about another different and quite interesting part of parameterized algorithms, which called kernelizations or kernels, right? And of course, my plan here is I will just speak a little bit about what is a kernel, and I give a very simple examples, and I probably will not go even further. Like that, okay, depends how fast we will go. Okay, so what is a kernel, right? If you make a search a kernel, even in Wikipedia, you will get a lot of different answers, right? So basically, the kernel, what I will be talking, this is a kernelization, a technique for designing efficient algorithms. Yes, so it's, but it's not any other things which you use like a general concept that includes kernel and linear algebra, category, or whatever. Okay. And so visualization of kernelization, if you really want to see, like, so if you're a sculptor, so what distinguish a good sculptor from the bad sculptor, right? So if you're a bad sculptor, you start immediately, you're trying to make sculpture immediately. But if you're a good sculptor, you see, look at the stone, and then you realize what you have to delete from the stone to make your sculpture. Right? It's just a different ways of seeing things. And this is basically what kernelization is doing. It's the way to understand what you can remove from your input to make it, to keep only essential part, which is interesting, which is computationally challenging. So some examples which I don't know how to analyze, but I don't know if you play chess, for example, there's also a lot of chess problems. And for example, can white checkmate here in 2 moves? Right? So it's a mental experiment. I don't know. Okay, that's okay. So yes, right. So what you do, right? You go from here. This is a check. So the king should move here, and then you use here to mate, right? But can you try to analyze how you think about this? Okay, that's yes. But basically, what I want to that when you think about this, at least to me, usually you somehow start thinking immediately. Okay, you don't try to move all kind of figures or pieces on the board. You think, okay, it should be something funny should happen around the black king. Right. So basically, it looks like you unconsciously concentrate only on the most important part of the board, and then you realize that all other pieces are useless for the game. Right? But how to formalize this way of thinking? No, right? So the other thing is actually is goes preprocessing, what we are doing also a lot in computer science, but also in real life, right? Like even for Sudoku games. So basically, when you solve Sudoku, it's not like you try to put all possible combinations, right? You will even with this simple instances. Instead, what you're doing, so well, to experience, you already know several set of rules we should try to apply. And if you're not experienced, you immediately invent the rules and try to apply them. And then you simplify the instance just by making some set of rules. And also, of course, in computer science, preprocessing is ubiquitous. So if you look at almost any reasonable algorithm which works in practice, you have to do preprocessing to simplify your instance. Even like in linear program solvers like simplex, navigating systems, and just a lot of examples. Okay, but we are doing theoretical computer science. Can we try to capture the notion what is a preprocessing and to build some complexity or a theory of complexity of preprocessing? And for example, take your favorite NP-complete problem. And the question is, can we say that for your favorite NP-complete problem, there is a preprocessing algorithm that guarantees, right? Because we always speak about worst case complexity, so we want the guarantee. If there's an algorithm that guarantees that it reduces every instance of the problem, say by 5%, Exactly, you'll say it's complete rubbish, right? That's what I'm saying, because like exactly. So if there's such an algorithm, what you do, you take your preprocessing, you reduce the instance, apply again, and at the end you find solution or yeah. But so in polynomial time you solve a complete problem. Doesn't make sense at all, right? Okay. So at first glance, there's no interesting theory for preprocessing of hard problems. Okay, let me argue with you, just give you an example, and then we'll come back to the more theoretical and parts. Okay, so this is an example of point line cover. I have set of points, n of points in the plane, and I have an integer k, parameterized problem, and I ask if I can find k lines that cover all the points, right? And here is my just reduction. First of all, I can assume that there are at most n square lines which I can use, right? Because no points to use more, right? Yeah. And then my reduction rule is the following. So I look at a line L which covers more than k points, if there exists such a line. If there exists such a line, I have to take it, right? Because if I don't take it, I will not be ever able to cover these points by other lines, right? So I have to take this line, I remove all the points covered by this line, and I reduce my parameter k by 1. Okay, so why the rule is sound? Well, yes, this I already explained. Yes, and at each step of reduction rule, we obtain a problem with smaller number of points. And thus, at the end, we either end up with a problem where no points left, and then we found a cover, we are happy, we say yes. Or the parameter k becomes 0, but some points are left. In this case, we don't have any solution, right? Or, that's the most interesting case, we arrive at the problem for which our reduction rule cannot be applied. What's happening in this situation? Okay, let's just try let's try to stare at this problem, right? Okay, so I know that no k plus 1 points can be covered by one line. How many? And I know that I have. I always say that. So how many lines I can have at all in my instance? Well, I'm claiming that if I have if no line can cover more than k points, then my instance should contain at most k square points. And look what happened here. So I still was able to define you some preprocessing rule, and I still was able to tell you that I'm able to reduce my instance to some value of the parameter. So when I speak about NP-complete problem directly, and I speak about the instance size, and I want to reduce it, I cannot say anything reasonable. But when I speak about parameterized problem, it's perfectly makes sense. And actually, yes, again, it doesn't. This problem is NP-complete, by the way. So, but it still doesn't show me that P is equal to P, because even I have an instance with k square points to solve this problem optimally, I still need to spend exponential number of time on that. And this brings me to the definition of the kernel. So what essentially happened? In polynomial time, my algorithm was polynomial. This reduction rule is polynomial. So I reduce my instance pk to an equivalent instance p prime k prime, such that the size of the p prime is bounded by a function of parameter k only. This is the definition. And then this is the definition, what is a kernel? Okay, so here is a formal definition of the kernel, and I really hate the formal definitions. So I will go very fast through it. So it's what it is. It's a kernel. It's a preprocessing algorithm, and this preprocessing algorithm, it works on parameterized problems. So I take a parameterized problem. It's an instance input, and this is the parameter. And then I construct an equivalent instance, and the size of this equivalent instance is bounded by some function of the parameter k here. And yes, and this is the definition of the kernel. So the two things. That should be a polynomial time algorithm which produces equivalent instance, and the size of the new instance should be bounded by a function of the parameter only. Right? So it's a polynomial time algorithm. But the only difference is that usually polynomial time algorithms, the usual polynomial time algorithms, they always give you some solution, number, matching, whatever, right? And this algorithm, it doesn't give you solution. It gives you another instance, but of smaller size. Yes. Okay, and then when the size of the new kernel is polynomial, we say that this is A is a polynomial kernel. Yes, and the usual thing that, because we now speak about polynomial, maybe we'll speak about exponential, so we always measure the size of the kernel as it's a number of bits, but often it's people specify what is this, the number of vertices, the number of points, the number of lines, clauses, etc. Okay, so now speaking this kernel language, I can say that point line cover admits a polynomial kernel with k-square points. Right? Any questions so far about a definition of the kernel? Okay, but so far as I define the rule of the games, now we're looking for polynomial time algorithms which do these interesting things. Okay, let's try to look further, right? What we can do with this type of algorithms. But before, let me just give another example. Vertex cover again, our favorite problem, and also you can also ask me why I always speak about vertex cover. I was speaking about branching algorithm for vertex cover, and actually the answer here is very simple. So first of all, vertex cover, it looks like it's a Drozdov-Filler of parameterized algorithms. It's NP-complete problem, but if you look at all NP-complete problems, not all of them are equal. Some of them are more complicated and some of them are simpler. And it looks like vertex cover is the simplest of them. Of course, it's a statement which I will not be able to prove, but usually my experience tell me that if I have a technique which works for some problem, with a good chance it should work for vertex cover. So for explaining algorithms, vertex cover is the best. So okay, so kernel for vertex cover. Again, so I don't give definition of vertex cover. Hope you remember it, right? Okay, so my theorem is that vertex cover admits a kernel with k-square edges and k-square plus k vertices. Okay, the proof. Okay, I just give the proof. I will just give you the algorithm. First, algorithm consists of a set of reduction rules. So the first reduction rule, if I have a vertex of degree 0, I just remove it. That doesn't make any sense to keep it, right? It doesn't cover anything. Okay, if I have a vertex of degree more than k, that's the interesting rule. What's happening here? If I have a vertex of degree more than k, you remember I was always saying that vertex cover should contain either vertex or its neighborhood. But if the size of the neighborhood is more than k, if this vertex is not on the vertex cover, I am forced to put all neighborhood in the vertex cover, and I run out of my budget k. So if I have a vertex of degree more than k, I always enforce to put this vertex into vertex cover, because the size of my vertex cover is at most k. So I reduce my instance, I remove this vertex, and I decrease the parameter. That's the new instance. Okay, and then my claim is that if I cannot apply rule 1 and rule 2 anymore, then my instance, a reducible instance, will have at most k-square edges. How come? Yes. So okay. So how come? So if okay, I have a graph. This graph, every vertex in this graph is of size is of degree at most k. Right. And also I know that the vertex cover of this graph should be also at most k. Sorry, once again. Okay, once again, what I'm saying, every vertex in my graph is of degree at most k. So it means that every vertex in vertex cover covers at most k edges, right? So it means I cannot cover with k vertices more than k square edges. So if your graph has, if your irreducible graph has more than k square edges, you immediately say no, right? That's the algorithm. I constructed equivalent instance, which has at most k square edges. And then you can also, yes, because it has at most k square edges, you can also say that it has at most k square plus k vertices. Okay, so that was one example of the kernel. And another example of the kernel, let me give you exponential, example of exponential kernel. And the problem is h-click cover. So input again, graph G and integer parameter k. And the task is to decide whether edges of G can be covered by at most k clicks. Some edges could be covered by several clicks. I don't care here, right? Okay, so here is an example of the k-click cover, right? So it's one click, another click, and the third click, all edges are covered. Okay, the theorem that this problem admits a kernel with 2 to the k vertices. The proof is the following. So first of all, if I have a vertex of degree 0, again, I just delete it. They will not be able to cover anything. Okay, now the following, the twin rule. If I have a h, u, v, yes? Yes, this is the problem. Okay. Again, so I want to find a set of clicks such that every h belongs to some click. And of course, click cover always exists because the set of edges of the graph, it's their clicks, right? They cover everything. But you are asking if you can have a smaller set of size k, which covers everything. Okay, vertices of degree 0, they're harmless, useless, we delete them. And now the main reduction rule is the following. If I have a h, u, v, such that the closed neighborhoods of this h are the same, so the closed neighborhood is it's vertex and itself, right? So basically the situation is the following here. U, v. So they, yes, they are like total twins, right? Yes. So then what I do, if I contract this h uv, or if uv was an isolated h, I decrease k by 1. That's the okay. So the claim is that both rules are sound. Well, the first rule is sound, is obvious, right? So why the second rule sounds? Well, look, imagine, so if I have 2 vertices with the same closed neighborhood, there is always a click which contains both of them, right? And if I cover, and now you have to follow, to give the formal arguments to show that if you contract an h, that this click in the graph covers all. So sorry, this click will cover the same set of edges if and only if. So you have to be a bit formal here, or just trust me here that if you're doing this, you don't create any problem, right? Okay, but then what is the size of the irreducible yes instance here? Okay, well, let's take a look. So suppose it's a yes instance. So this yes instance, it can be its edges could be covered by at most k clicks. Yes, I construct the following binary vector for every vertex v. I construct a vector, k-dimensional vector. Basically, it's characteristic vector. So the coordinate of this vertex, of the vector xv I is 1 if and only if the vertex v is contained in the click ci. Right? So it's yes. Now the following observation is: if I have vertices which are, if I have 2 vectors which are equal, what does it mean? Right? It means that, by this definition, right? So that they have exactly the same closed neighborhoods. Now, because I was applying the first reduction rule, right? I was removing vertices of degree 0. I know that each of these vectors is non-empty. And now, which means that if two vertices are twins, okay, once again, what I'm saying here. So if I have two vectors are equal, right? How this could happen, right? So then, so by definition, they should have the same neighborhoods, right? No, that they should have the same neighborhood. Yes, because once, so either they are twins or they should be empty, right? But they cannot be empty, and also they cannot be twins by the second reduction rule. So it means that all these vectors should be different, right? But each, there's a one-to-one correspondence from vertices of the graph and the vectors. Agree? Right? This is by definition. And also all the vectors are different. So it's, and the dimension of the vectors is k. They're binary. So there are at most 2 power k of such vectors. So this means that there are at most 2 to the k vectors. And this means that there's at most 2 to the k vertices in the graph. Right? This means that this irreducible graph has at most 2 to the k vertices. That's it. Okay, so okay, so far, okay, we speak about parameterized problems, and for parameterized, if you have a parameterized problem Q, we have one of the following options so far, right? We know that what could happen. Q admits a polynomial kernel, could happen. Q admits just a kernel. The kernel could be of exponential size. And also, maybe it could happen that the problem Q doesn't admit kernel at all. Right, so I show you one example of this problem. I show you one example of this problem. And for that problem, there are also the problems which have this property. But to understand what if the third question about so if the problem doesn't admit a kernel, let me just make a simple observation. First of all, if my problem admits a kernel, this implies that the problem is FPT. Why? Because what is a kernel? I have a problem. I reduced the size of the instance to some function of k. And as far as we always speak about discrete problems, right? So you give me a discrete problem, I can use brute force, try all possible instances or solutions in this problem, so and have FPT algorithm. So kernel implies FPT. A bit surprising thing that if the problem is FPT, then it also admits a kernel. This is a theorem. So if the problem is FPT, then it admits a kernel. And when you see the first time this proof, this proof is a bit like cheating. Okay, let me just give this proof. So deciding, so my problem Q is FPT. By definition, deciding if I have an instance I and K, so the pair, deciding if this is a yes instance of Q. So it could be done in time f of K times some polynomial of the input length. This is by definition. Okay, so by some algorithm A. I don't know how this algorithm looks like, but I know that this algorithm exists. Now, what I'm doing, I will give you now a kernelization algorithm. This is my algorithm A, and I run my algorithm I power C plus 1 steps. This is a polynomial number of steps, right? Because C is a constant. So I run this algorithm, yes. Now, if my algorithm does not terminate, I output just the initial solution. I claim that this is a kernel. Why? Because what does it mean that, okay, so I run my algorithm this time. So if my algorithm terminates, it's find a solution, I'm perfectly happy, right? It's yes or a no. I solve the problem. That's fine. If I didn't solve the problem, right, so it's still working, what I know that the running time of my algorithm, f of k times e to the c, because I know that this running time is sufficient to solve the problem, then this f of k times e power c is strictly larger than e power c plus 1. Right? But this means that f of k is larger than I. This means that if I just give you the input itself, the input size should be bounded by some function of k. Right? So it's okay. So then coming back to this question. So if you ask the question about kernelization, so if your problem admits a polynomial kernel, if a problem admits a kernel exponential, or this question, if the problem admits no kernel, it's exactly the same. Is your problem is fixed parameter tractable or not? Yes. Yes, no. Once again, I just follow the definition. What I know, if the problem is fixed parameter tractable, then I know that there exists an algorithm A. Yes, there exists an algorithm by definition, right? It's okay. And then I just, I have no idea actually what is this algorithm A. It's yeah. Okay. Okay, let me just give one more example of kernelization algorithm. And again, that's the same deheating set problem, which we looked the first hour. And you remember, for three heating set, we were very successful. What I did, we took the algorithm for vertex cover, and we just generalized this algorithm very easily to work for heating set. Let me just try to implement the same strategy and to see if we manage to do it or not. Right? So what we did for vertex cover, you remember, right? We were taking the vertex of degree more than k, and we were saying that this vertex should be in the vertex cover. So here maybe we could have the same. Like if I'm trying to solve this problem for a heating set, if I have an element which is contained in k plus 1 sets, and then this element should be in the solution. Right, so then I'm trying to imitate the same type of kernel for heating set, and yes, but unfortunately I need to do a bit more, right? If I have an element which contains in k plus 1 sets, then I know that this should be in the solution, and if I have two elements which are contained in k plus 1 sets, then also at least one of them should be in the solution. Right, and this creates me. Okay, I can even make reduction rules. So, like, first of all, I deal with isolated vertex elements. Then, if I have an element of high degree, then I can delete this element and create a new instance. Or if I have two elements, then I can say that these two elements they form a set, and delete all other sets which I can cover, which I hit by them. And basically, this is an algorithm, but and then the unpleasant question is, okay, I made the algorithm, but what will be the result of this algorithm? Right? What will be how many sets will be in the irreducible yes instance? And basically, the answer here is that it should be k cubed. But if you really want to prove it, actually, I was really curious. I did it. But the proof becomes very messy because you have to consider a lot of different cases. And yes, so I skip very fast I will not give you the proof, and I skip fast through that. But the point, what I want to make here, look, we are working with a very basic combinatorial problem. It's a heating set problem. And people were looking at this problem from many angles, not for hundreds of years, right? But from 1950s for sure. And basically, one of this point I want to make, before jumping into solving the problem, yes, of course, you are brave and you want to attack, and that's understandable. But first, think about other people who also thought about this problem. And this is actually this is a classical problem in extremal combinatorics. And there are very beautiful combinatorial results about set cover. And if you know these nice and beautiful combinatorial results, you don't have to do any mess with case analysis. That will be a very beautiful and very cute argument how to obtain a kernel for set cover. Okay, and this is a nice, beautiful theorem from extremal combinatorics. This is sunflower lemma. So what is a sunflower? Again, a sunflower is if I have a case sets S1, S2, Sk, they form a sunflower if all guys Si, if I take the common intersection of all of them, remove them, then remaining subsets will be entirely disjoint here. And this is, so the jargon here is that these sets are called the remaining, so the common intersection is the center of the sunflower, and the remaining parts are the petals. So here is example of a sunflower. I have 4 elements, and this is the common intersection, these 2 elements. This is a sunflower. And the beautiful lemma of Erdős and Radó from 1960s says that if the size of the set is greater than p minus 1 power d times d prime, so I'm speaking here about set, every set is of size at most d, right? Then this set of systems should contain a sunflower with p petals. Furthermore, actually, this is there exist constructive proofs of this statement, and there's a polynomial time algorithm which computes the sunflower. So basically, once again, what the lemma says, you take a lot of 3 heating sets, and there's really a lot of them. Somewhere in this mess of 3 heating sets, there exists a nice sunflower. Right? So how to use this lemma algorithmically? So reduction rule. If I have a k plus 1 sets which form a sunflower, then I remove these sets from the family, and I add a new set which consists of the center of the sunflower. Yes. So the lemma says that if you have more than p elements, or more than this amount of sets, then you always have a sunflower with p petals. Right? Sorry? Yes, yes. So, but every set has at most d elements. Okay, so what are the arguments? Okay, look, and this is more or less exactly the same argument as for the vertices of high degree, right? You remember. So if I have for vertex cover, if I have a vertex of degree more than k, this vertex should be in the vertex cover. The same argument is here. If I have a sunflower with k plus 1 petals, then at least one vertex from the center should go to the heating set, right? Because if none of the vertices from the center goes to the heating set, I still have to hit all these sets, but all of them are disjoint. So I have to use k plus 1 vertex elements to hit all these petals and run out of budget. Okay, so then what I'm doing, so then if I found such a sunflower with k plus 1 petals, I encode the information that I have to take at least one guy from the center into the heating set. And how I do it, I just make a new set which consists of all elements of the central elements. And then I don't need anymore these petals, because I will never use these guys probably, right? I will never use the sets. I don't have to cover the sets anymore. So I remove this set. Okay, and yes, if the center is empty, the sets are disjoint, then of course there's no solution, right? Because I have k plus 1 disjoint sets. Okay, and if I cannot apply this rule, my claim is that I have at most k power d sets. Right? Why? Why? Because I'm using the Erdős and Rado lemma, right? Which says that if I have more than k power d plus if I have more than k power d sets, then I should have a sunflower. And then I can apply reduction rule, which means that if I cannot apply reduction rule with a sunflower with k plus 1 petals, then the number of total sets should be at most k power d. Okay? So in essence, it's the same degree reduction rule, but in a much more nice and cuter, stated in a much nice and cuter way. Okay, so as a home exercise, I want you to construct a polynomial kernel for D set packing. So it's a problem as a dual to the heating set. So here I have a universe U, I have a family S of sets of size at most D over this U and integer K, and I'm asking if there exists a subset X of S of size K such that all these sets are pairwise disjoint. So on this example, I have a packing of size 2. Right? This guys are disjoint. Yes. And again, so here you view, when I speak about polynomial kernel, I view D as a constant. And the hint is, again, try to use the sunflower lemma, but it will require one more observation for doing this. Okay, so yes, to conclude, so I just give you a very fast glimpse of what kernelization things. Yes, and this area is relatively new to compare to parameterized algorithms and to compare to general set of classical algorithms. But still, there are already a lot of work happened here, and there are also quite nice and interesting and quite deep mathematical methods for obtaining kernelization techniques. And also, there is a companion complexity theory because, but complexity theory here it makes sense. Okay, I was saying that there are 3 variants: either polynomial kernel, either exponential kernel, and there's no kernel at all, right? If there's no kernel at all, it's the same as is the problem fixed parameter tractable. So the whole theory of parameterized complexity works here. It doesn't make sense to make a new theory. But there's a nice complexity theory which distinguishes polynomial kernels and exponential kernels. So for example, the problem k-path. We had a FPT algorithm for k-path. But it's possible to show that unless something strange happens in complexity theory, that there's no way to construct a kernel polynomial for k-path, for example. So there's yes, and if you really want to learn more, first of all, the introduction to kernelization is the chapter 2 of the blue book. It's and then if you want to go into more details, the squirrel book is also will give a lot of things about kernelization. Okay, I stop my lectures here. If you have any questions, please do it now, during lunch, or today. Yeah.
Okay, let's thank the speaker.